All right, so let us begin. Last class we talked about some properties of absolute value, right? And then we see the triangle inequality and other related things, right? So we see the triangle inequality and other related things in the last class. So, and then I briefly introduce you about the natural numbers. So today we are going to talk about the natural numbers and some of the related topics related to natural numbers. So right, so this is the first thing. So far we know that there is a 0 and there is a 1 in the real number system, right? So that is basically you already know, right? So now what we are going to define is right. So we are going to define a set A in the which is basically a subset of a real number system, a real number set, right, with the following properties. The first thing is 1 is a member of A. So 1, you know, it is a multiplicative identity. So it is a member of A. And also if X is a member of A, then X plus 1 will also be a member of A. Right? So this is something you see in mathematical induction, right? So you prove the first step and then you take the K step and go to K plus 1 step. That is what you do in mathematical induction, right? So here we define a set like this, right? 1 belongs to A and X belongs to A implies X plus 1 belongs to A, right? Right, so this kind of set we name it as inductive set, right? So that's how we define the inductive set, right? An example for this is right. So for example, all positive integers, right? 1, 2, 3, 4, 5, that basically give you an inductive set, right? So similarly, you can think of different inductive sets, right? So by using this inductive set idea, right, we shall define the natural numbers, set of natural numbers. Right, so let us define curl M, right, which is a collection of all inductive sets in real number, right? So here I gave you one example, positive integers, right? So there are other similar type of sets are there, right? So then you can get any such collection in the inductive set, right? Right, so the intersection of all possible inductive sets in R, right? The intersection of all possible inductive sets in R is defined as N, right? We call it the natural number, right? Right, so this N is the smallest inductive set in R, right? So you can easily say that, right? So we shall try to prove this, right? The following way. Right? So first we have to show that N is the inductive set, and then we have to show it is the smallest, right? So to prove this, because M is an inductive set, right? M is an inductive set. You know, 1 belongs to M, right? Right. So clearly, 1 belongs to the intersection of all possible inductive sets, right? That's not a big thing to do. Right? Next, you have to show that if X belongs to N, then X plus 1 also belongs to N. Okay, so next thing, you have to show if X belongs to N, right? So X belongs to N, right? So that means X belongs to M for all M in curly M, right? So that means, right, because M is an inductive set, right? So X plus 1 belongs to M for all M belongs to this curly M, right? So if X plus 1 belongs to M for all M, then clearly X plus 1 belongs to N, which is actually the intersection of M. M belongs to curly M. Right, so we prove that 1 belongs to N, and also if X belongs to N, then X plus 1 belongs to N. So N is an inductive set. Right, so by using the basic set theory notations, we prove that if 1 belongs to N, so we prove that 1 belongs to N, and also if X belongs to N, then X plus 1 belongs to N. Right? So we prove that by proving these two, we prove that N is an inductive set. So next what we have to do is we have to show that n is actually the smallest, right? So it says this is the smallest set. So let us take an arbitrary set. Right, so let P be any inductive set. If P is an inductive set, then you know P belongs to this curly M, and because curly M is the collection of all inductive sets. So if P is an inductive set, it should be a member of M. Right? But N is actually the intersection of M belongs to curly M of M, right? But N is a intersection of all sets, right? All inductive sets in M, right? So the set of all inductive sets which are members of curly M. So clearly P is a member here, so that means this is contained in P, right? Because intersection of all sets is a set that is contained in each of the sets, right? So that you know from very basic level. Right? So if you have two sets, let's say A, B, and C, right? The shaded part is actually A intersection, right? A intersection B intersection C. So that itself is a subset of A, and itself is a subset of B, and it is basically a subset of C. Right? So then this intersection is a member of P itself. So N is a subset of P. Right? So we show it for an arbitrary set, right? So hence right, so clearly N is the smallest inductive set. So that's the thing we have to prove here, right? We define N as the intersection of all inductive sets, right? Then clearly it is an inductive set itself, and as well as it is the smallest inductive set. Right? So we prove. Okay. So now what we are going to do is we are going to show you what you are doing in mathematical induction actually works, right? So that is what we are going to prove next, right? So I will write this as a theorem. Right, so this is the principle of mathematical induction. This is what you use in A level, right? So here, so in A level, what you do is you just say that if you want to prove a results by induction, what you do is you just say, okay, for n is equal to 1, the result is true, and then you take for n is equal to k, the result is true, and then you prove the result is true for n is equal to k plus 1. And hence you say that by mathematical induction the results is true for all n, right? But you didn't know that whether that actually correct how that results come, right? So here what we are going to do is we are going to actually prove that the mathematical induction is a true statement, right? So that is what we are going to do. So let's say okay, so let's say Pn be a proposition, right? For all or for every n belongs to natural number, right? Right, so this is the mathematical induction. You have a proposition Pn, and which is true for P1, right? Which is true for n is equal to 1. And if it is true for n is equal to for some n, then it will be true for n plus 1 as well, right? So if those two conditions are satisfied, then we can say that Pn is true for all n in natural number. Right? So we shall prove this by using the inductive set and the other properties of natural numbers which we just studied. Okay, so what we are going to do is we are going to define for this proof. Right, so we will define a capital M, right, which is the set of all n, right, such that n belongs to natural number as well as Pn is true. Right, so clearly you define M as a set of all numbers for which the statement is true or the proposition is true, right? So that's what we have here, right? So first thing we notice that clearly you can say that the capital M, the set, is a subset of natural numbers because all the elements are coming from the natural number set, right? So set of all n such that Pn is 2, so then basically they will be those will form a subset of natural numbers. Now we will try to show that it is an inductive set, right? So right, you clearly know 1 belongs to a natural number because we already proved that in the last theorem of proposition, right? 1 is a member of n. And here it is given that P1 is true. So obviously 1 will be a member of capital N. Right? So this gives me 1 is a member of capital N. Right. Next. If you take n, arbitrary n belongs to M, right? Then you know clearly n is a member of natural number set and also Pn is true, right? If n is a member of capital M, then you can say that it is true. But N belongs to natural number, but you already proved that natural number set is an inductive set, right? The last exercise we proved that it is an inductive set. So this gives me n plus 1 belongs to natural number, right? Because n belongs to natural number, we already proved in the last theorem, n plus 1 belongs to natural number. And here it is given, if Pn is true, then Pn plus 1 must be true. Right? According to this theorem, the hypothesis of this theorem tells me that if Pn is true, then Pn plus 1 is true. So this gives and Pn plus 1 is true. So now you can see that n plus 1 is a natural number and Pn plus 1 is true. So obviously n plus 1 will be a member of M. Right? So n plus 1 will be a member of M. Right? Okay. So once you do that, that says, right? You now have what you have. You have 1 belongs to M. And then here, if n belongs to M, then n plus 1 belongs to M. So this tells me that M is an inductive set. Right? So this tells me that M is an inductive set. So if N is an inductive set, right, you know that it is a member of curly M, right? So that's clearly we know. But the previous results, we say that natural number is the smallest inductive set. So natural number should be a subset of M because M is an inductive set, but by previous results we already know that natural number N is the smallest inductive set, so clearly N should be a subset of M. But according to our definition, M is a subset of N, right? So we have two results, both of them are true. M is a subset of N, but at the same time N is a subset of N. So that means M and natural number should be equal, right? So then only you can have one is the subset of the other and vice versa, right? So that is possible only for two equal sets. So that is why you have M is a subset of N as well as N is a subset of N. So M is actually natural number. So this means what? M must be equal to N, but M is defined as the set of all N such that Pn is true. So therefore, Pn is true for all natural numbers. So this gives right. So then Pn is true for all N belongs to N. Okay, right. So this is why the mathematical induction works in all your proofs or all your proofs and other works in the A level, right? Because of this statement, right? So if these two are true, then we can clearly prove that Pn is true for all natural numbers. So that is why you are able to do those exercises or examples in mathematical induction. So now I will give you a couple of exercises as homework, right? Where you will try to prove something using mathematical induction. Exercises. Right, so these are the two exercises. If m and n are natural numbers, then m plus n is a natural number, and also m times n is a natural number, right? So for this proof, I give you a hint, right? Right, so here two natural numbers are there, m and n, right? But you know your mathematical induction is only defined for one natural number, right? So here there are two natural numbers involved. So what you can do is both of them are arbitrary natural numbers. So what you do is you fix one natural number and let the other be an arbitrary, so that you can easily apply the mathematical induction. Right? So then clearly you can define a statement Pn, right, as n plus n belongs to natural number, and then prove it by mathematical induction. Here also you fix m and say the statement as P of n as m dot n belongs to natural number, and then you can prove it by induction. Right, so that's how you prove this. Right. So now right, so now right. So here that is what you are trying to prove, right? So by using mathematical induction, you can show that n plus n is a natural number and n times n is a natural number. Right. So now what you have is this. Right, so this is what you do, right? We start with 0, 1, and then we have x. From x you have x plus 1, so that means you build up 2, 3, 4, and so on, right? So basically you have integers, right? Non-negative integers you define, but you have to go to the negative side as well, right? So if you want to go for all real numbers, then you have to define the other things. So here what we are going to do next is we will try to define the other type of number systems, right? So these are just definitions, so let me write them down. Oh, let me say in that's given in your notes. Use that. Okay, so here what we did is we started with 0 and 1, and then basically we define a set 1, 2, 3, 4, 5 and call it as natural numbers, right? So once you know them, right? 0. So this is what we did. We started with 0, 1, and then we define n, which is basically 3, 4, right? So these are the sets we define and we call it natural number set, right? So, but at the very first axiom, right, the algebraic properties of numbers, we see that additive inverse, right? If a is a number or a is a real number, then you have minus a there in the real number set, right? So because you have 1, 2, 3, 4, 5, 6, that means you will have the additive inverse for those numbers as well. So you will have -1, -2, -3, -4, -5, and so on as well. And they are also members of real numbers. So you take that collection, the additive inverse of each natural number, right? So that will form a negative integer set, right? So we call that set as negative integer set, right? So those are -1, -2, -3, and so on. Okay. So now you have natural number, you have negative integers, and then you have 0, right? So if you combine all of them, right? Natural numbers, negative integers, and zeros together, that form you a set, right? Which is called as integer set. That is 0, 1, 2, 3, and then -1, -2, -3, and so on, right? So all the way here down to negative infinity and all the way up to positive infinity. You take all integers and name that as z. Once you have integers, you have positive, negative, even integers and odd integers. Right? 2, 4, 6, 8, 10, -2, -4, -6, -8, -10, and so on. Right? So these are even integers. They are multiples of 2. Right? So 2, 4, 6, -2, -4. So 2 times natural numbers, 2 times 1, 2 times 2, 2 times 3, and then so you have positive even integers, right? Sorry, I put natural numbers. These are integers, right? So these should be integers. You have positive and negative, right? So that is why it should be integer. Right? So -2, -4, and +2, +4, so on. And then odd numbers 1, 3, 5, 7, -1, -5, -3, -5, -7, and so on. Right? So that's 2n plus 1. They will be in the form 2n plus 1. So those are odd integers. We define or denote them by ZE and ZO respectively. And then here is the relationship, right? Natural number is basically a subset of integer, and integer is basically a subset of real number. And at the same time, odd integers and even integers are respectively subset of the integer set as well. Right? So these are some other type of numbers which are members of real numbers, right? So we start with 0, 1, and then positive integers, negative integers, odd integers, even integers. So we have basically the integer numbers, right? But there are other types of numbers as well, right? So you know that you have fraction, right? 1, 2, 3, 4 also you have, but 1 upon 2, 1 upon 3, 1 upon 4, 1 upon 5, 2 upon 3, 2 upon 4, 2 upon 5. All these numbers are there also. Right? So we will define them. Right? Those are called rational numbers. Okay, so these are called rational numbers. Right? Right, so elements in the set R, right, that can be written in the form P upon Q.
Element.
Right, all elements that can be written in the form P upon Q is called right. So all elements that can be written in the form P upon Q are called rational numbers, right? So we denote that by Q. Right, so let me write it down here. Right, so capital Q with it's a line there. That is the notation for rational numbers, right? That means any number that can be written in the form P upon Q for P integer and Q natural number, right? So that's how we define rational numbers, right? Right, so here usually, right, when we write rational numbers, right, we mostly write them as simple fractions, right? So that means the greatest common divisor of P and Q is 1, right? So there is nothing else other than 1 be a common factor of P and Q, right? Because obviously, they are. So you can say 2 upon 4 is also a rational number, but that you can write it as 1 upon 2, right? So 2 upon 4 is also a rational number, but this is actually 1 upon 2, right? So we don't usually write 2 upon 4. We write, right? So we write it as 1 upon 2. Okay, so that's the usual procedure. So that is what given here, right? So whenever you write the fractions, you try to write them such that the denominator and the numerator has 1 as the greatest common divisor, right? So that's how we do it. So now we start with natural numbers, and then we move to integers, and now we come to Q, rational numbers. But you already know there are other type of numbers as well, right? So for example, square root of 2. You learn about square root of 2 already, and at least for certain digits you know the value, right? Even our calculator can do that. Or square root of 3, square root of 5, cube root of 3, cube root of 5, right? So all these things you have learned, at least you get to know these numbers, right? Those numbers cannot be written as fractions, right? So square root of 2, you cannot write that as P upon Q, or square root of 3, you cannot write that as a P upon Q. So there are numbers which are not rational, right? So there are still some real numbers which are not rational. So we call it irrational numbers. So basically Q complement, right? So Q is rational, so it's Q complement, right? So we call it, it is basically R set minus Q. So everything in the real number except rational numbers are called irrational numbers, right? So for example, cube root of 5, right? The lot of values are there. So these are irrational numbers, right? So these are irrational numbers. Okay, so these are the number systems, so these are the type of numbers you have, right? So basically you have this, right? So actually you start with natural numbers, and then you go for integers, and then there are rationals, and then there are irrationals, and all of them together forms to real numbers, right? So this is how we define the number system, right? So if you want to see it as a set, right? So basically right? So basically, if you look at this, natural number is a smaller set, and integers is a larger one that contains natural number, and then rational numbers actually contains all the integers and little bit more, right? Fractions, because you know 1 is also 1 upon 1, right? So 2 is 2 upon 1. Minus 3 is minus 3 upon 1, right? So those are also fractions, and you can, if you like, you can write them as fractions as well. So in that case, so integers can also be a subset of rationals, and then everything outside is basically rationals, right? So there are some other numbers as well which are known as transcendental numbers, such as e, pi, and things like that, but that's a little too much for you, so we will stick with rationals and irrationals and real numbers, right? So this is how we define the number system, right? So first thing is, I will give you a homework just to see whether you will be able to do this or not, right? So here I say that irrationals are the numbers that cannot be written as a fraction, right? So irrational number is basically q complement, right? That means you cannot write that number as a fraction, right? So right? So you have to, as an exercise, you try to show that square root of 2 is a irrational number, right? So I will give you a hint, right? Right, so basically what you have to do is you have to show that you cannot write down square root of 2 as a fraction p over q, right? So if you want to show that something is an irrational number, then you have to show you it is not rational. So you have to show that it cannot be written as p over q. So basically you try to write square root of 2 as p over q, and then try to see whether you get a contradiction or not, right? So I will leave that as an exercise for you to see some books or some other related stuff and try to prove these things, right? So in the next class, we are going to talk a little bit about geometric representation of numbers, and then we will try to talk about the completeness axiom, which is one of the important sections of this course, right? So we will try to focus on the completeness property. Basically, we will start it tomorrow, right after talking a little bit about integers, right? So I will stop here, and then we will continue tomorrow at 1.